Hey everyone, I am your friend Shadab Imam and we are continuing our lecture series on operations research. If you are new to the channel, please subscribe the channel and don't forget to hit the bell icon. So today we are continuing our lecture on the two-phase method. So let us begin with the problem, and the problem says that maximize z is equals to 5x1 minus 4x2 plus 3x3 subject to constraints 2x1 plus x2 minus 6x3 equal to 20, 6x1 plus 5x2 plus 10x3 less than equal to 76, 8x1 minus 3x2 plus 6x3 less than equal to 50, and x1, x2, x3 greater than equal to 0. Now, as we have discussed in the previous lecture, in two-phase method, what we do is we will separate the problem in the two parts. In the first phase, we will try to eliminate the artificial variable or to drive the value of artificial variable to 0. And in the second phase, we will go for the optimal solution. Now, let us first convert this into standard form. So, let us convert the constraints into standard form. So, this will be 2x1 plus x2 minus 6x3 plus a1. Because there is equal sign, so we will introduce an artificial variable here equal to 20, and 6x1 plus 5x2 plus 10x3. This is less than equal to sign, that means we need to introduce an slack variable here. So this is s1 slack variable is equals to 76. Similarly, for the third equation, we have 8x1 minus 3x2 plus 6x3 plus s2 is equals to 50, and x1 comma x2 comma x3 comma a1 comma s1 comma s2 all should be greater than equal to 0. Now we have seen that to solve the first phase we need to find an artificial objective function. Okay, so artificial objective function here will be to minimize the artificial variable, minimize z dash I am taking equal to a1. Now in order to solve the problem, we will convert this minimization objective function into maximization and write it as maximize z dash is equals to 0x1 plus 0x2 plus 0x3 plus 0s1 plus 0s2 minus a1. So this is our new objective function, or I should say the artificial objective function. These are constraints. So let us start solving. So first of all, we'll write the objective function. This will be x1, x2, x3, s1, s2 and a1 with objective function coefficient as 0, 0, 0, 0, 0 and minus 1. Now in order to find the variable in the basis column, we need to put the values of x1, x2, x3 equal to 0. So in the first equation, if we put x1, x2, x3 equal to 0, we'll get a1 is equals to 20. Similarly, s1 is equals to 76, s2 is equals to 50. That means all the three are non-negative and they are eligible to enter the basis column. So this is variable a1, this is s1, this is s2 with objective function coefficient minus 1, 0, 0. Now we'll write the constraint coefficient, which is 2, 1, minus 6, 0, 0, 1 equal to 20. Similarly 6, 5, 10, 1, 0, 0 is equals to 76, and 8 minus 3 6 0 1 0 equal to 50. So now we have prepared the initial matrix and we need to find the values of Cj minus Zj. As we can see, this will be minus 2, minus of minus 2 is plus 2, so this will be plus 2, this will be plus 1, minus of minus 6 plus 6, this will be minus 6. Okay, similarly this will be 0 0 and 0, because s1 s2 and a1 are the basic variables and they will attain value 0 in Cj minus Zj row. Now we will select the maximum positive value here. So 2 is the maximum positive value, so this will be our key column and it indicates that variable x1 will now enter the basis, and to find out the leaving variable we need to calculate the value of theta, which is right hand side value divided by corresponding key column element. So 20 divided by 2 is 10. Similarly 76 divided by 6 is 38 by 3, and 50 divided by 4 is 25 by 4. Okay, so now among these we need to find the minimum positive value. So here we can see that 25 by 4, this is the minimum positive value, so we will select this as the leaving variable and this will be our pivot row. This indicates that variable s2 will leave the basis and x1 will replace s2, and the value 8 here will be our pivot element. So let us write here variable a1, variable s1 and variable x1, because x1 has replaced x2. This will be minus 1 0 0. Now we need to make this as 1 and the remaining values in the column as 0. To make this 1, I will divide the row 3 by 8. So this will be 1, this is minus 3 by 8, this is 6 by 8, that means 3 by 4, this will be 0, this is 1 by 8, this is 0, this is 50 by 8, that means 25 by 4. Similarly, now in order to make this as 0, what I will do is row 1 minus of 2 times row 3 or new row 3. So row 1 minus of 2 times of new row 3, this will give 2 minus 2 is 0, this will be 1 minus 3 by 4 is minus of minus is plus. Okay, this will be 7 by 4. Similarly minus 6 minus of 3 by 2, this will be minus 15 by 2, this will be minus 15 by 0, minus of 2 times of this is 0, 0 minus of 2 times of this is minus 1 by 4, 1 minus 2 times of 0 is 0, and 20 minus 2 times of this, that means 20 minus 25 by 2, this will be 15 by 2, 15 by 2. Similarly, I need to make this element as 0, so I will take row 2 minus of 6 times new row 3. Okay, row 2 minus of 6 times new row 3. So this will be 6 minus 6 is 0. This will be 5 minus 6 times of this. This will be 9 by 4. 9 by 4. 29. Okay, this will be minus of minus plus. So this will be 29 by 4. This is 29 by 4. Similarly, 10 minus of 6 by 4, so this will be 9 by 2, 40 plus 9, this will be 11 by 2, this will come as 11 by 2. 1 minus of 6 times of this is 1, 0 minus of 6 times of this is minus 3 by 4, this will be minus 3 by 4. 0 minus 6 times of 0 is 0. 76 minus 6 times of 25 by 4 is 77 by 2, this will be 77 by 2. Now we need to calculate the, sorry, this will be 1, okay, this will be 1 minus 0 is 1, okay. Now we need to calculate the values of Cj minus Zj here, and we'll have the value 0 0 0 for x1, s1 and a1 because they are in the basis column. And let us find out these value. Minus 7 by 4, minus of minus is plus, this will be plus 7 by 4, minus 15 by 2, this will be plus 15 by 2, minus, and this is minus 1 by 4 minus 1 by 4, this will be 15 by 2, so I am not calculating the value of Z here because there is artificial variable appearing in the matrix, so I have not calculated the value of Z in both the matrix. As we can see now that there is one positive value appearing in the Cj minus Zj row, so we will now select this as our key column, and this indicates that variable x2 will now enter the basis. And to find out the leaving variable, we need to again calculate the value theta, which is right hand side value divided by corresponding key column element. So 15 by 2 divided by 7 by 4, this will be 15 by 7, 30 by 7, this will be 30 by 7. Similarly 77 by 2 divided by 29 by 4, so this will be 154 by 29, this will be 154 by 29. And as this is negative, we do not need to calculate this. Instead we will put a dash sign here, that means variable x1 is not eligible to participate for the leaving variable. Okay, so among these two variables we need to see which one is the least positive. So as we can see that 30 by 7 is the least positive value here, so this will be our leaving variable and this is our pivot row. That means now variable x2 will enter the basis and it will replace the variable a1, and among them this is our pivot element here. So now let us move further. x2 has replaced a1, this is s1 and this is variable x1. The objective function coefficient are 0, 0 and 0, and now we need to make this 7 by 4 as 1 and the remaining values in the column as 0. So I'll divide the row 1 by 7 by 4, so I'll get the value as 0 by 7 by 4 is 0, 7 by 4 by 7 by 4 is 1, minus 15 by 2 by 7 by 4 is minus 30 by 7. Similarly 0 by 7 by 4 is 0, minus 1 by 7 by 4 is minus 1 by 7. This is 4 by 7. 15 by 2 divided by 7 4 is 30 by 7. Now in order to make these values as 0, what I'll do is I'll take row 2 minus of 29 by 4 times new row 1. So 0 minus 29 by 4 times of 0 is 0. This will be 0. 29 by 4 minus 29 by 4 times of 1 is 0. 11 by 2 minus of 29 by 4 times of 30 by 7. So we will have here the value as 256 by 7. So this will be 256 by 7. Similarly have 1 minus of 29 by 4, so this will equal to 1, and minus 3 by 4 minus of minus 1 by 7 into 29 by 4, so we'll have here 2 by 7, and 0 minus 4 by 7 into 29 by 4, this will be 29 by 7, or I do not need to calculate the value here. Here also we do not need to calculate the value, because artificial variable has left the basis, and once we know that once artificial variable left the basis, we do not need to calculate the values of artificial variable further. So we are not calculating here the values of artificial variable. So moving ahead, this will be 77 by 2 minus of 30 by 7 into 29 by 4, and this will give the value as 52 by 7. 52 by 7. Okay, now in order to make this value as 1, what I'll do is row 3 minus plus 3 by 8 times of row 1. Row 3 by 8 times of row 1. So this will be 1 plus 0 is 0. This will be 0. 3 by 4 plus 30 by 7 into 3 by 8. So this will be minus 6 by 7. This will be minus 6 by 7. Similarly 0 and 0 is 0. 1 by 8 plus minus of 1 by 7 into 3 by 8. So this will be 1 by 14, and we do not need to calculate the value for artificial variable. Similarly here 25 by 4 plus 30 by 7 into 3 by 8, this will be 55 by 7. 55 by 7. Now once we have calculated the values, we need to check for optimality by calculating the values of Cj minus Zj. So again there is some mistake, this will be positive. Okay, so for all the basic variables, the Cj minus Zj value is 0, and here we can see that value of x2, x1 and s2, this will come as 0. Similarly here also we will get the value as 0, and the value of z is coming as 0. So here we can see that all the values here are coming as 0. That means we have finally found our optimal basic feasible here, and we will now use this particular solution in the phase 2 with the original objective function. So in order to use this, I am just erasing this first matrix. So I am erasing these values here, and I am writing the final matrix again. So and our objective function will also be changed. The new objective function will be here. So I'll write the original objective function, which is 5x1 minus 4x2 plus 3x3 plus 0s1 plus 0s3. So this will be 5 minus 4 3 0 0, and here once our artificial variable has been removed, we do not need to consider artificial variable to be calculated further. Now as we can see here, these are our basic variables x2, s1 and x1, and the original coefficient of these are -4, 0 and 5. And now I am exactly replicating this in the first phase, in the first matrix of the phase 2. So this will be 0 1 minus 30 by 7, 0 minus 1 by 7, and similarly 0 0 256 by 7, 256 by 7, 1 and 2 by 7. For the third it is 1 0 minus 6 by 7, 0 1 by 14, and the right hand side values are coming as 30 by 7, 52 by 7 and 55 by 7. Now we need to calculate the values of Cj minus Zj to find whether this particular solution is optimal or not. And remember that right now we are solving phase 2 of the two-phase method. This is phase second of the two-phase method, where we have started with the matrix that has ended in the phase 1 solution, and we have taken this because we have no artificial variable here. So we can take this matrix as the first matrix of phase 2. Now let us calculate the values of Cj minus Zj. So we can see that x1, x2 and s1 are basic variables. They will attain the value 0. Now we will calculate this. This will be 120, this will be minus 30, this will be 90 by 7, 3 minus of 90 by 7. So this will come as minus 69 by 7. This will come as minus 69 by 7. Similarly for S1, this will be plus 4 plus 5 9 plus 4 double 8 plus 8 9 17. So this will come as minus 13 by 14, and the value of Z will come as minus 120 plus 5 into 55 by 7. So this will come as 155 by 7. So as we can see here that now all the values in the Cj minus Zj row are either 0 or negative, and the value of Z is coming as 155 by 7. This shows that we have got our final optimal solution, and in this solution, according to this solution, the value of x1 is coming as 55 by 7. The value of x1 is coming as 55 by 7. x2 is coming as 30 by 7, and x3 is coming as 0 because x3 does not appear in the final solution. So the value of x3 is 0, and the Z max is coming as 155 by 7, 155 by 7. Okay, so this is our final solution. And now we need to understand something, that at the end of phase 1 we can see that there are more number of zeros than we have variables in the basis column, and this does not mean that we will now going to enter any other variable here, because we need to understand this, that as soon as we are eliminating our artificial variable or the artificial variable attaining the right hand side value as 0, then we will stop iterating further. Okay, then we will take this as the final solution and we will move to the phase 2 where we will use the current or the final matrix of the phase 1. Again I am saying this, that once our artificial variable has been eliminated or our artificial variable attains the right hand side value as 0, we will stop iterating further in phase 1 and we will take that solution as the basic solution and start with phase 2. As in this case, our artificial variable has been eliminated here, so we have taken this matrix and we have moved to the phase 2 and we will take this matrix as the starting matrix or the starting solution for phase 2, and we will iterate further as we do in basic simplex. So we will solve one more problem regarding the phase two-phase method, and if you like the lecture, please share the lecture. Have a nice day. Thank you.